did Marilyn want me to zoom this? Does she want me to zoom this? Okay, I'm going to record it then. Yes. When you're done looking at your tasks, if I can get them back, please. I haven't actually written down the marks yet. Huh? Oh. Okay, does anyone else still have their test? Okay then, do we have any questions on any of the KEQ math? Or is it straightforward-ish? Straightforward-ish? All right, in that case, we are going to go back to shifts and stresses. So we are heading to, where are we heading to? We are heading to 2.2C, page 38. Page 38. Joshua, you dropped something on the piece of paper. All right, page 38, volume and pressure are inversely proportional. Good, we all need that. So in other words, as volume decreases, the pressure increases. Yes. Go with inversely. I don't know what indirect, I don't know. I should never have mentioned it in grade 9. Just forget I ever said anything. Yes? Okay, I'll go talk to a math teacher. They probably know. An inverse is specifically a 1 over. Actually, I do know. Inverse is specifically 1 over x. I think indirect is when one goes up, the other goes down, but it's not a 1 over x because 1 over x looks like this. Is that right? Yes? Whereas an inverse can look like, or sorry, indirect can look like that. Yes? Okay. I think that's the difference. Don't get too wound about it. It's not going to be that important in chemistry. Talk to your math teacher if you're concerned about it there. All right, so here we have a system. We have nitrogen and hydrogen coming together to make, yes, Casey? 1 over x, you go from, oh, why are they? Because because they are related by P1, V1 is equal to P2, V2. Yes, you remember that one? I forget whose law that is. I think it's Boyle's law. Okay. And so if we are looking at P2, if we solve for P2, P2 is equal to P1 times V1 over V2. So if our volume has increased, so if this got bigger by, let's say, 2 times, then this is going to get smaller by 2 times. Yes? So, and this is what it looks like if you graph 1 over x. Does that make sense? Cool. Okay. I'm shocked I was able to pull that out of my head, but anyway. If we decrease the pressure, volume, what happens to the pressure? If we decrease volume, pressure increases. And if pressure increases, what happens to the forward reaction? The rate of the forward reaction. The rate increases. Why? Greater frequency of collisions. What happens to our reverse rate? It also increases. Am I recording? I am. Yay. Whew. Okay. Whew. Which rate is increased more? The forward or the reverse? The forward is going to be increased more. And it is because the side with more gas molecules experiences a greater rate of change. And if we look, how many gas molecules are on the left-hand side? In red, 4 gas molecules. And over on the right-hand side, how many gas molecules? 2 gas molecules. So whatever effect is felt, it will be felt more by the side with more gas molecules. And the reason for that is that the rate is dependent upon the concentration, yes? And we are affecting the concentration of more things, yes? So, therefore, the forward rate, which has more gas molecules, will experience a greater increase. Do we want to go through this whole thing? Sure. Okay. Why does the direction with the most gas molecules as reactants experience the greatest change? Let's think about what happens when we have the volume. That's HALVE, when we have the volume, not when we have the volume as in owning it. Okay? So, if I have 4 gas molecules and I have the volume and I go from 1 liter to 0.5 liters, I go from having 4 molecules in 1 liter to having 4 molecules in 0.5 liters. So I go from having 4 molecules per liter to having 8 molecules per liter. So what was the change in concentration of molecules in general? I went from 4 to 8. So the change was 4 molecules per liter. All right. On my other side here, I have only 2 product molecules, yes? When I have the concentrate or the volume, I go from having 2 molecules per liter to 2 molecules per 0.5 liters, which means I now have 4 molecules per liter. Are we following? Okay. So the change was 2 molecules per liter. So here we compare now our 4 with our 2. Which change was greater? 4. So we had a greater change in the concentration, therefore the forward rate is affected more. And in the reverse rate, we had a smaller change in concentration, therefore the reverse rate was affected less. Are you ever going to have to be able to explain this and draw the pictures and do all of that? No. You just need to know that the side with more gas molecules as reactants, that direction is affected more by a change in pressure. Okay, so the forward rate therefore is increasing more than the reverse rate. So what has happened to both rates? They have both increased, but since the forward rate increased more than the reverse, I'm going to put that in here. The forward rate is therefore greater than the reverse rate, meaning we are no longer at equilibrium. We now have a forward rate greater than our reverse rate. Which way are we shifting if our forward rate is greater than our reverse rate? We are shifting right. Since we are making products faster than we are using them up, so the system is shifting right. Honestly, I don't believe on an AP exam you're going to be asked to explain the shifts via rates, but I could be wrong. You know what I mean? And plus, it's also good to understand what's happening in terms of rates. If you prefer a less visual but more mathematical representation, you can look at this. We go from 4 to 2 to 4. Do we care? Should I have just left this page out? I could have left this page out. Oh, well, that's okay. All right. So a greater amount of gas molecules caused a greater change in concentration when the volume is changed. So we have a greater change in rate on the side with the greater number of gas molecules. And that means that the forward rate increased more. So if we are filling in our original rate, that would be like here and here. And then after we've decreased the volume, we would be like here and here. Is that looking like what you would expect? All right. Therefore, the forward rate is greater than the reverse rate. I feel like I'm repeating myself a lot. Is this too repetitious? Is good? Okay, okay. So that makes, so we are making products faster than we are using them, therefore we are shifting to the right. Okay. So we're now going to we're now going to graph what happens when we decrease the volume. Now, you are never on an AP exam going to be called upon to graph the concentrations because we're going to fudge them a lot. Okay, so, but this is kind of like, you just need to kind of know what happens. So if we're doing a rate diagram, what goes on the x-axis in a rate diagram? On the x-axis, time or progress of reaction. And on the y-axis, rate. We're going to have our forward reaction rate and our reverse reaction rate. And we are starting at equilibrium, so those two rates should be equal. Excellent. And now we decrease the volume. What happens to our forward rate? It spikes. Yes, it does. What happens to our reverse rate? It also spikes. Does it spike by the same amount? No, more or less. It spikes by less because it is affected less because it has less gas molecules, so the change in concentrations is less great. So here we go. Now, so I'm going to just show it somewhat less. I sometimes like to draw myself a dot here so that I can tell when I'm going from stress to shift, okay? It just helps me. You don't have to worry about it if you don't want to, okay? What do the rates do now? Forward rate decreases. What shape? A curve, an S curve? No, not an S curve, okay? And what does our reverse rate do? It curves up. Now, do you remember when I said there were corners? You should always have a sharp corner. Well, you'll notice we do not have a sharp corner here because it was going up and now it goes up some more. Okay, but that's all right. As long as you are going, as long as you have it steep at the beginning and shallower and then flat. Steep, shallow, flat. Yes, that's the key thing. We don't actually need that corner if we have increased and then the shift also causes an increase. All right, that's lovely. Shall we do a concentration diagram? Again, time down here, but now we have concentration on the x-axis. Remember, my initial concentrations are set arbitrarily, okay? I'm just picking where I put them. And now we're going to decrease the volume. What happens to all the concentrations? All the concentrations increase. All concentrations increase. And you'll see why I'm going to fudge this, because I'm going to draw something on here and then I'm going to erase it, okay? What if I halved the volume? That would mean I would have to do what to every concentration? I would have to double it, which would mean that this one would have to end up here, which is really awkward, yes? We would like our graph to all fit in one plane. So rather than trying to double this one and then double this one and then double that one, we're just going to show them going up like this, okay? So I know it is not accurate, but we just need to show that all of those concentrations go up because we've decreased the volume. It doesn't matter. Doesn't matter. Just like show them going up by any amount you like that's convenient. I usually just try and make it so they don't overlap one another, but I've still got some room to play. Okay. So now, which way are we shifting if we decrease the volume? We are shifting to the right because remember the forward rate increases and the reverse rate also increases, but not by as much because there are fewer gas molecules. Okay, so we are shifting to the right. So my concentration of NH3 should go NH3 if I'm shifting to the right, up. Okay. So I'm actually going to put this in a different color. I'm going to draw my dot there because it went up and now it is going to go up some more. So I'm putting that dot there to remind myself that was my stress. Now we are into the shift. What happens to our H2? It goes down by how much? Half the amount of the NH3. We've got 3H2, so that's going to be a factor of 3x, yes? Yeah, it's all good. The NH3 is going to go 2x, and the N2 is going to be x. Does that seem familiar from like the KEQ calculations that you did on the weekend? Yes? Okay. So this one is going to now go down because we are shifting to the right, and it's going to go down by 3x. So what I'm going to do to help myself out here is I'm going to say that's 2x. And so I want the H to go down by 3x because I suck at drawing things. So I'm going to be like, well, there's 1, 2, 3. That's approximately where I want it to end. Because I can't do it in my head. If you're good at art and you can just visualize those things, then you go for it. I am not good at art. Here we go. Okay, and I'm trying to have them level out at about the same time. I don't think I quite succeeded there, but if you were to draw something like this, I would say close enough. Yes? And then N2, will N2 go up or down? It's going to go down by how much? Little bit? Like what? How many x's? 1x. So it needs to end up about here. And that would be a bad graph. I would not be happy with that if you drew it on a test or quiz, what is wrong with that line the way I drew it? It's going up, so I would need it to go across like that, okay? There we go. Okay. The change in volume makes all the concentrations change. So every time you have a change in volume, you will change all the concentrations. And all the concentrations will change in the same direction, because if you squish one of them, you're squishing them all. Yes? And if you expand one of them, you're expanding them all. Okay. And note 2 is just telling you why. That's just explaining we're not going to double everything because it falls off the graph if you do that. And the changes due to the shift should be proportional to the coefficients. We knew that. Good. Ooh, look, there's a little simulator here. Do we want to try it? Do we care? You can try the simulator at home if you want to. Yes? I'll let you do that because I would have to actually go find the document. So here we go. Here's a little picture. 2A in equilibrium with B. Why does it say increase the volume, decrease the pressure? Because that looks like it got smaller. That's the wrong way around. Decrease the volume, increase the pressure. Okay. Is yours correct? Okay. Okay, so here we go. We decrease the volume, we increase the pressure. So the stress was an increase in pressure. Therefore, and this is looking at it in more of a Le Chatelier's kind of way. So let's look at our pictures. Here we have some molecules happily spread out. Yes? Now they are squished. Ah, that is their stress. How are they going to unstress themselves? They're going to shift to the side with less molecules so they have more space again. Yes? So we increase the pressure, the system is going to shift so that the pressure, overall pressure, will decrease. Once again, that is a Le Chatelier's explanation. The stress was an increase in pressure, so the system will shift to decrease the pressure, which means it shifts to the side with fewer molecules, because fewer molecules will decrease the pressure. That's not an actual reason why, but it helps you predict the direction of the shift. Okay? So there was an increase in pressure, so the system shifts to the side with fewer gas molecules, which is the products. You go from 2A to having only 1B. So it's going to shift to the right. This will bring the total number of moles of molecules to make it smaller. So the smaller total moles of gas will bring the pressure back down. Fewer gas molecules mean fewer collisions with the side of the container, and therefore the pressure will decrease. So according to Le Chatelier, what is Le Chatelier's principle? Tell your partner. Hi. Yeah. That's fine. Yeah. I'll be posting the lecture
later. So you, actually, if you need to go home, you can just go home. Okay? Yeah. So Le Chatelier's principle, when a system at equilibrium is stressed. The system, yes. Thought I heard you say it, yeah. The system will shift in order to minimize the stress. So if you are ever asked to define Le Chatelier's principle, that's a pretty darn good definition. Do not define it as what you do, nature tries to undo. However, if you're trying to think of it, you can think of it as whatever you do, nature tries to undo. So if you make the pressure go up, it's going to try and make the pressure go down. If you increase a concentration, it's going to try and bring that concentration back down. And if you increase the temperature, the system's going to shift to try to decrease the temperature. So anything you do, nature will try to undo. But that is not a definition that you ever want to write anywhere. It's just a way of thinking about it so you can remember it easily. Okay? Okay, here we go again. And now we are increasing the volume. Decreasing the pressure. I got the label right this time, that's exciting. So the system says, oh, what has happened to the pressure? The pressure got smaller. So I need to shift to the side with less molecules to make the pressure go back up. I need to shift to the side with more gas molecules to make the pressure greater again. So you can see what's happened here is that we have shifted from the gray stuff to the red stuff. Yes? We've shifted to make more. And I actually did go through here and make sure that all the reds and grays worked out numerically. I don't know if you can appreciate that, but I went through and I removed as many reds as many grays as would make that many reds. So, at any rate, the stress was a what in pressure? Decrease in pressure. Therefore, the system will shift to the side with more. One of those two. More gas molecules, i.e. in this case, that would be to the left. And that means we're going to have a greater total number of gas molecules, which will bring the pressure back up, since more gas molecules mean more collisions with the sides of the container. That means our pressure has increased. We good? Cool. Okay. So this is just sort of summarizing the whole thing. So if we increase pressure by decreasing volume, since the overall space is decreased, This is a rate explanation. All of the particles collide. If the overall space is decreased, all the particles collide. Hold on, if the overall space is decreased, more frequently. Therefore, what happens to both the forward and reverse rates? Both forward and reverse rates increase. The direction with more gas molecules will have a greater or lower? Greater increase in rate, since the concentration of gas molecules is affected more. Therefore, the direction with more gas, reactant gas molecules will be faster. If you want to say more faster, you can say more faster. Okay, sometimes I like to do that, even though it sounds stupid, just to be like, okay, everybody got faster, but this one got more faster. Okay, therefore the system is shifting away from the side with more gas molecules. Like I said, the chances of you having to explain things in words like this on AP is slim to none. Yes? It's really about you understanding what's going on. Yeah? What if we decrease the pressure by increasing the volume? The overall space is increased. Since the overall space is increased, all the particles collide less frequently. So both the forward and reverse rates, what do? They decrease. However, the direction with more gas molecules as reactants will have a larger or greater decrease, since the concentration of gas molecules is affected more. Therefore, the direction with more reactant gas molecules will be slower. And if you wish to say more slower, you may do so. Okay, more slower. Therefore, is the system shifting towards the side with more gas molecules or away from the side with more gas molecules? Towards the side with more gas molecules. That one makes my brain hurt even a little bit, but that's okay. Like I said, you're not going to have to write this explanation. Now, what if there's the same number of gas molecules on both sides? Because that does happen like fairly frequently. Both rates will increase equally. And there will be, you'll still be at equilibrium. There's going to be no shift. Okay, you will see a spike in all the concentrations, but you will see no curve / shift. Okie dokie, so if we were to, did I draw graphs on the next page? Was I clever enough to have done that? Okay, I did on the next page, so that's fine. So I won't cram drawings onto that page. and then have them in the page afterwards. So, Le Chatelier, you are much more likely to have to explain a shift in terms of Le Chatelier when we're talking about pressure, because like I said, the rate explanation is unwieldy. Do you guys know that word? Unwieldy. Unwieldy, it means awkward and hard to manage. Okay, did I spell it right? I might have spelled it wrong. It might be IE. Anyway, doesn't matter. So if the stress was an increase in pressure by decreasing volume, the system is going to shift to the side with less gas molecules to bring the pressure back down. Like I said, one of those two, right? But by saying it aloud, you're actually activating lots of parts of your brain that don't get activated if you don't say it out loud, so that's actually very smart. The stress, if the stress was a decrease in pressure by increasing the volume, then the system will shift to the side with more gas molecules to bring the pressure back up. And once again, if there are the same number of gas molecules on each side, shifting will not be able to counteract the change in pressure. So there will be no shift. No shift. You will see a spike, but no curve. And let's graph this. Graphing with the same number of molecules on each side. Here we have a rate diagram, so our rate is here. This is a concentration diagram, so our concentration is here. I'm just going to use time because it's easier to write than progress of reaction. So if we had this system here, H2 plus I2 gives 2HI, and if we increase the volume, here's our forward rate, here is our reverse rate. If I increase the volume, what happens to the rates? The rates decrease, both of them. Now, which side decreases more? Trick question, right? That's why you're looking at me like, what's wrong with you, Ms. Spence? Yes, it is a trick question. They both decrease by the same amount because there's the same number of gas molecules. I got 2 here and I've got 2 there. So the forward rate is going to go down. The reverse rate is going to go down. Because the 2 rates are still equal, is there any shifting? No, they are now just generically slower. Yes? Singing helps me draw. All right, now our concentrations. What happens when our volume decreases? What happens to our concentrations? The concentrations all decrease, yes, because we're now in more space. So they are all going to go down, and we're not going to worry about how much because otherwise HI might fall off the bottom of the page, okay? And they would overlap each other and it'd be awkward. Now what? Yes? Okay. Ooh, exercises. Okay. We're going to actually move on to 2.2D and start on it. Yes, Joshua, sorry. Yes? Oh, did I not label the axes? Oh, no, we don't need to worry about that here because that decrease wasn't due to a shift. It was due to the stress. And remember, I'm being unrealistic in how much the concentrations change due to the stress, because otherwise what would happen is that H2 would actually end up down here. And then our diagram looks terrible because everything's overlapping each other. Yes? And you can't really keep track of things because if it got halved, then H2 would be here, and I2 would actually end up here. And then I'm like, and where is everything? It's just too much. Yes, I need to keep them separate so that they don't look like a huge mess. Yes? Why do they go down by more? They don't go down by more. They would go down by less. So if HI went down by this much, right, because it got halved, that's about half, yes? Then I2 would also be halved, which would take it to about there, right? Now, my problem is now I've got overlapping lines, which is ugly, yes? And if my H2 was also halved because because I doubled the volume, then my H2 would look like this. Do you see how that looks nasty because all the lines overlap? Well, if I take the volume and I multiply it by 2, then the concentration is going to go by 1/2. So here is, we've got this, now it ends up a half left at a half. Huh? It does not relate to the coefficients at all. No. The coefficients are for the shifting because the coefficients have to do with how they're actually reacting, not how many particles there actually are. With the number of particles there actually are, that's to do with the volume and the concentration in that. Yeah. Anyway, I'm sorry I've made a huge mess of that. I'll get rid of that. We'll just go la 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 la. There we go. 2.2D. We're not going to get very far through this. You can do 2.2C for homework, the questions, okay? This one we're just going to start on today because we need to keep moving. Rate perspective on changing temperature. Is the forward reaction here endo or exothermic? Exo, excellent. Is the reverse reaction endo or exothermic? Endo. Which reaction, forward or reverse, has the higher activation energy? The endo one, which would be the reverse. Are we good with that, or would you like me to draw the graph? You know what, I'm going to draw the graph anyway, because I put a little thing here, right? So we have an exothermic reaction. La 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 la. Yes? So the endothermic reaction, the reverse reaction, always has the higher activation energy. Is good? So what happens to my forward rate when I increase the temperature? Increases. Why? 1, more frequent collisions. Uh-huh. Okay, so we got those 2 reasons. That's nice. What happens to my reverse rate when I increase the temperature? It increases. Why? For the same reasons as here. Yes. Which rate is increased more? So here we have our a higher activation energy. Yes. And here we have the lower activation energy. You with me? Okay. If I have a higher activation energy, is that the endo or the exothermic reaction? That is the higher activation energy is the endo. I got to make this bigger so I can write again. Endothermic reaction. And in this case, the endothermic reaction is the reverse, yes? Direction. In our other graph, we have the lower activation energy, so that is the exothermic reaction. In other words, that would be the forward direction. Okay. And now we're going to do like a little ballpark of what percentage of the collisions are effective. Okay. So here, in our colder sample in the endothermic direction, I guessed that that was about 1/25th of the entire area under the curve. Does that sound reasonable? Like if I took that little triangle and I put those triangles into that area under the curve, would there be about 25 of them perhaps? Give or take 5 triangles, you know? Okay, so 1/25th. Now with my warmer sample, now I have about half, yes? About half the collisions have enough energy to be successful, okay? So in essence, we have increased our successful collisions by 50 divided by 4 is 12.5 times. Yes? By the way, you're never going to have to explain this. I'm just showing you why it works. Okay? Now, if we look at our exothermic reaction, we go from having the blue area, which is perhaps a quarter. Yes? Okay, so that's 25%. To the warmer sample, and I'm guessing that that one's about 2/3 of the area, which is about 67%. So we have had an increase in successful collisions of only 2.7 times. Yes? So which rate is affected more by a change in temperature? Endo or exo? Endo. Do you need to do any of this? No, but that's why it works. What you need to know is that the endothermic reaction rate is affected more, and it's affected more whether you increase the temperature or whether you decrease the temperature. Is that a good place to end today? Excellent. All right, so the one on pressure for homework.